Okay. Hello, and a very warm welcome to the Memorial Symposium of Professor Gerhard Kraetzschmar. As some of you may recall, it is now more than a year ago that Gerhard has left us. We, as colleagues, friends, former PhD candidates, comrade in arms, students, and relatives, very soon thereafter came up with the plan to conduct a symposium in his memory. We decided to try to shed some light on his impact and activities, not only at our university at Bonn-Rhein-Sieg, but also on national, European, as well as international scale in communities focused around institutions like ICAPS, ICHCAI, AAAI, and EU Robotics, the George Giraud Award, or various EU frameworks where Gerhard has served frequently as an expert reviewer. My name is Paul Plöger from Hochschule Bonn-Rhein-Sieg, and I will be your host during this week-long summit of robotic talks to commemorate Gerhard. We are very happy that it was possible to appoint speakers from all around the world, reaching from Japan over Europe to the US. So please allow me to briefly introduce you to the time format of the symposium, as well as to our speakers. Each day of the week, from Monday till Thursday, there will be a talk of the respective expert. These talks will start at 10 o'clock in the morning, European Central Time, summertime actually, except on Thursdays, where we will have a speaker from the US, and due to the time delay, it is necessary to start late in the afternoon at 1600. On Friday, the very last day, there will be a full wide collection of tasks all day long. We'll start with 4 tasks in the morning and continue with 4 more presentations during the afternoon. The symposium will end with a roundtable at Friday late afternoon about the topic of robotic competitions and benchmarking, 2 topics which were of central importance to and heavily influenced by Professor Kraetzschmar in his scientific career. The tasks are conducted by a truly international group of speakers, namely on Tuesday by Itsuki Noda from ICE in Japan, on Wednesday by Dirk Holtz from X, the moonshot factory in Silicon Valley, on Thursday by Fernando Ribeiro from the University of Minho in Portugal, and then consecutively on Friday, Luis Almeida, University of Porto, Portugal, Gerhard Steinbauer, Technical University of Graz, Austria, Nico Hochgeschwender, Hochschule Bonn-Rhein-Sieg, Germany, Luca Gnocchi, Sapienza University, Italy, Daniele Nardi, Sapienza University, Italy, Manuela Veloso, former CMU, now on leave at JP Morgan AI Research, Pedro Lima, Universidade de Lisboa, Portugal, and finally, Matteo Matteucci, Politecnico di Milano in Italy. As mentioned, all these 8 talks will take place on Friday. Additionally, let me note here that the symposium is not an exclusively online one, since on Friday we will broadcast from our Audimax, Hörsaal 1, here in HBRS, and we are allowed to have up to 50 participants in there. Please feel most warmly invited to drop by, of course, following the usual precautions. Secondly, I would like to ask you for understanding and patience in case of glitches. Although we have been teaching online for more than 6 months by now, we are still no motion picture award candidates, so just be patient. And as all of you and we as roboticists will know, it will work ultimately. Lastly, let me thank some of our sponsors, since without their contribution to this event, it would not have come true. Most notably, the university as a whole, here especially Vice President for International Affairs, Professor Bode, the Dean of the Department of Computer Science, Wolfgang Heiden, as well as countless supporters from the department and the MIS group, Debul Nair, Mohammad Wazil, Iman Awad, Kira Watzinski, Mira Mutgandieri, and many, many more. Okay, now it's actually time to introduce our guest of today to you, who is going to be Professor Michael Beetz from the University of Bremen. He, in fact, is more than a colleague to Gerhard, since both of them have met as early as during their joint studies, and they kept in close contact ever since. Michael Beetz is now head of the Institute of Artificial Intelligence, IAI, which investigates AI-based control methods for robotic agents, which focus on human scale, everyday manipulation tasks. With his OpenEase, a web-based knowledge service providing robot and human activity data, Michael Beetz aims at improving interoperability in robotics, thus lowering the barriers for robot programming. Due to this, the IAI group provides most of its results as an open source software, primarily as parts of the ROS software stack. Okay, one very, very last note. You can actually ask questions during this live streaming to Professor Beetz. And for that, please visit our event website, or you do it via the YouTube comments. Okay, finally, Michael, I see that you're online now and ready to take over. Can you please now switch over to Michael Beetz and his talk? Hello, Michael.
Hello. Yes, I'm still working on the setup.
Okay.
So
no
I try to give my best.
What has been working before will also be working now.
Okay. So.
Here we go.
Okay, cool.
It's promising. So all the very best. I shut down my microphone now.
Yes, so thanks a lot for inviting me for this Memorial Symposium for Gerhard. And yeah, it's of course a great honor to contribute to this symposium. And we certainly still miss Gerhard a lot. And I think in particular in the evenings when we are around the robots and work on robots, I think we wait for somebody rumbling in, throwing a big backpack onto table and asking what's up. And yeah, so Gerhard is a very long friend, and it's almost 35 years ago when we actually started to work together, already as students of different universities, but we came together in a research lab of a typewriter company. So this was a time where basically the first AI hype was going on, and the typewriter company was joining from, was entering as a typewriter company, the artificial intelligence hype. And of course, in a company like that, there were no people, no engineers who could do any AI or program kind of symbolic programs or build knowledge representations. So at that point, I mean, the company hired students from very different places. I think one of the places was Kaiserslautern, where Professor Siegmund was giving one of the first proper lecture courses in AI, and from Darmstadt, and Gerhard from from Erlangen having attended lectures of Herbert Steuern. And I think the four of us were very dear friends for a long, long time. And we still celebrate almost every New Year's Eve together. So as you can see, the four of us, two of them became successful. The other two, Gerhard and me, became professors. And yeah, so we had a very great time. So as students, we had essentially the responsibility of carrying the research program of the company and work towards kind of an industrial knowledge representation and reasoning system that was supposed to help Triumph Adler to get into the next generation of his information system. So the knowledge representation system was called Ludwig, for Ludwig Wittgenstein. And as you can imagine, a typewriter company was not doing extremely well at these times. And so Triumph Adler was bought by Olivetti, and consequently Ludwig became Luigi. And a bit later, we actually joined in a cooperation with a British company called Harlequin, who developed as a first non-US company kind of a Lisp development and environment. And we were working together in getting parts of the knowledge representation and reasoning system under the label knowledge work into the company, into the Lisp framework. So this is notable because because LispWorks was also a company that ran the Lisp for the deep space mission of NASA. When there was the first autonomous flight. And so we can wonder whether actually parts of Gerhard's code were in use when the deep space mission of NASA was taking place and controlling the autonomous robot. So it already started that Gerhard was working on these very reliable autonomous systems. So as students, not even having the diploma degrees, we were very active and very involved in the research, and so one of the big events our first big event that we had together was attending the ICHCAI conference 1987 in Milan, where we basically saw for the first time all the researchers that we have read the papers of. And I think that ICHCAI conference, where we drove together in Gerhard's car to Milan, was memorable for all of us in multiple ways. So we had a concert in the Scala with all the computer science and AI nerds, and so that was memorable because, well, the researchers were told to actually bring jackets. So indeed, many of the attendees had jackets, but it was also the time when it was modern and fashionable to have neon jackets. So you can imagine a number of the American colleagues sitting with neon jackets in the Scala, and how that looked when the orchestra was playing. So this night at the Scala was not only memorable for us, it was also memorable for the ushers in the Scala. I think at that time, also as student, we had to look for cheap places to eat in the evenings. So we were in big groups going to a very cheap pizza, and we drank all the Bartolino that was available in that over the week. And so one of the lessons that I had to learn together with Gerhard was that actually drinking grappa out of water glasses when the owner of the pizzeria is serving them is not necessarily a good idea. I was also sharing an apartment with Gerhard, and of course that was mostly enjoyable. So to everybody who has had a breakfast with Gerhard or dinner, I can tell that the skills of preparing these huge breakfasts and dinners, it's not something that he learned late in his life, but that is a skill he had from early on. And the other thing that matched extremely well was that, as all of you know, Gerhard is a man of action, a doer. I'm kind of a little bit less efficient in acting and doing things. So the Germans would say I'm a little bit umständlich. So that fitted very well. But there were also kind of things that didn't fit that well. So for instance, the music taste. Probably also many of you know Gerhard had a very experimental music taste, and I think the music is only good if it's at full volume. I myself had the habit of singing under the shower in the morning, so I think that kind of in the music domain, it was more or less a draw. I think the other thing that also all of you probably have experience in one way or the other is Gerhard's strong skills in leading and winning discussions. So we had many discussions when we lived together about everything, and it's difficult to remember one discussion where Gerhard had the same opinion as I had. So in particular, I think he most of the time made up his opinion after I have actually stated mine before, and it was always the opposite one. Yes, so one of the kind of discussion points where he didn't win the discussion, and I think that kind of might have been the only one, is in terms of whether for AI researchers it's actually necessary or it's necessary to attend RoboCup and compete in the competitions, right? And so I always had the feeling that the research problems in AI are so open, and we have so huge problems in front of us that actually going into competitions is a waste of time, and that we should rather work together on the open problems in open research communities, where Gerhard was pushing certainly the competition as one of the kind of most important approaches in order to forward research. Yeah, so the first time that I experienced Gerhard in the RoboCup community and how leading his position was in the field was probably at RoboCup 2001 in Stockholm, I believe, in the midterm league. And that was very remarkable and impressive. So at that point, there were many of the leading researchers in artificial intelligence, like Manuela Veloso and Daniele Nati, and they were the leading scientific researchers in the field. But seeing them at a RoboCup competition was a very different experience, right? So it was a lot of complaining about decisions that the referees took and how unfair they were, and pushing the own team. And I remember one case when I believe Daniele was going to Gerhard, and he was complaining about the referee and that he called a foul in one situation, and Gerhard answering, "Oh, what a foul! If I was the referee, I would have sent him off the field, and not only him, but all the robots acting in the team." And yeah, so it was always funny, and it was very interesting to see the researchers involved in the RoboCup activities. Gerhard also afterwards had kind of substantial impact in promoting the software engineering for robotic agents. So I think his main activities started at the University of Ulm, where he was doing or leading the robotics activities, the autonomous robotics activities in a collaborative research center that aimed at integrating symbolic and subsymbolic information processing in adaptive sensomotoric system, kind of a topic that could as well be the topic of a research center today. And at that time, he was developing with the doctoral students, he was advising kind of a very impressive middleware system called Miro, I think, which was substantially used by the community. And he also founded the RoboCup team, mid-size team in Ulm, the Ulm Sparrows. I think Gerhard was also very influential in building various research communities. So for one thing, of course, the RoboCup community that I was less involved in, but also the robotics community in Europe that was forming around the ideas of cognitive robotics. So there he was very active in a research project called BRICS, which is best practices in designing robot control systems, where he also organized summer schools and other events to teach the doctoral students in Europe how to program robots. And in other projects like RockEU, he was doing the community service for organizing the roadmaps for European research in robotics, and Skyrock developing further the scientific robot competitions. And I think it's very rarely that that you have researchers that that contribute to the field in such a comprehensive way, on the one hand on the research side, but also on the community side, and in particular also at the on the student side, helping the students to develop and evolve into researchers. And I think probably that is I think one that might even be the biggest impact that Gerhard had and is having on all of us, I think. So even more so than in RoboCup, and that is the way he brought up the students and developed them into researchers. So I think in some ways Gerhard was very much like a father. He was very challenging when he was interacting with a student. I think it was not always a pleasure for the students to give a practice talk before conference talks. But I think he also supported all the doctoral students in kind of a very comprehensive way in all dimensions of life, and helped them to develop their competence and skills. And to the outside, when he was talking about his own students, they were always the most brilliant ones, the most talented ones. So, and I think he had a kind of a very sustainable impact on the career of many of his students, and I admire him for that a lot. Okay, so that is what I wanted to say about Gerhard, and I would now talk a bit about the scientific aspects, and I want to talk about the use of artificial intelligence techniques, and in particular knowledge representation and reasoning for developing robot control systems for the real world. And I think in particular having research contributions that can be embodied into real-world robots and solve real-world tasks was a topic that Gerhard was always pushing a lot, and I hope he would enjoy that talk. So. Okay.
After many years of research, we're now at a stage where our robots can perform complex manipulation tasks, but only in specific contexts, for specific objects, and under specific conditions. The transition should be to mastering human-scale manipulation tasks in realistic and open situations. If we want to go from current robots to mastering activity robotics, the key point is knowledge. The robot will only get key point task descriptions, such as drop something from the pot, and it will need to know that it means tilting the pot, that if it tilts it too much, it will spill, not too high, not too low, and that the weight in the pot will change. The question is, how to get the common sense and naive physics into robot control systems and make it effective. so that it basically does its job without delaying the performance. The robot should not have to wait a long time until the reasoning problems are solved. The reasoning should be ubiquitous, so fast that you don't notice that it's there.
Yes, so as we have seen, when we have robots acting in the real world, the key problem is how they achieve underdetermined action description. So if you look at an action request like perform a pouring action with where you basically pour out the water from a pot. So if a robot has to execute that task, it has to infer a lot of detailed information about the actions. And in particular, it has to infer how it has to move its body in order to accomplish such a task successfully. And making that inference about the body motion that it should execute requires a robot to infer motion parameters such as it has to grasp the pot by the handles. It has to hold the pot horizontally. It has to tilt the pot around the axis between the handle. It has to hold the lid while pouring, and many other of these problems. And of course, kind of the big question that we have if we are investigating intelligent autonomous robots is, where do we get all that knowledge from? And how did we get that knowledge actionable within a robot control system? So my research group and me are working on a cognitive robot architecture that is targeting in automating this kind of problem. So the cognitive architecture consists of a plan-based control system that uses very general plan, like fetching any object from any place and placing it at any other place. And that plan executive that is using a knowledge representation and reasoning system. And that knowledge representation and reasoning system is acting a lot like the Siri agent of the iPhone. So what is happening if the plan executive is executing a general abstract plan? It always asks, how do I take kind of a general description of an action it should execute, and how it should generate the respective body motion in order to accomplish the task. And the knowledge representation has to return a motion specification, a specification of how the body should move, which is then executed by the plan executive. So why is it that kind of robots have to reason about motions? So if you think about it, so what we want to do is we want to specify actions and how they are to be accomplished in a very general way, so that we don't have to reprogram the robot control system for every particular situation. So what we want to have is we want to have a general plan schema that basically fetches and places any object that is located at any place and places it at any specified destination. And the way this abstract plan should work is the following way. So we simply say that at the location where the robot believes the object to be, the robot should fetch the object. And at the location where the robot is intended to be located, it should place the object. So what we are doing is we basically get that we have one general plan for accomplishing all fetch and place tasks, because we do a lot of hand waving, right? So we basically talk how that plan should be executed in a very abstract manner, and we don't talk at all about the specific details. On the other hand, we can look at the motions that have to be generated. So if you're looking at motion plans and the way humans execute motions, you can see that the motion plans of humans for executing manipulation tasks are very stereotypical, very rigidly structured. So an action like picking up an object and transporting it to another place is structured by researchers in the cognitive science area into a reaching phase, into lifting off the object, transporting it to the new place, and releasing it. So each of these motion phases have motion goals. And the motion goals are essentially force dynamic events that kind of the agent has to realize and achieve. So if I'm reaching for an object, my goal is to touch with my fingers the object to be lifted off. If I'm lifting off the object, the goal is that the object doesn't have contact to the supporting surface anymore. And the third aspect of these low-level motion plans is if we are looking at each of these motion phases, they have knowledge preconditions. So if I'm reaching for an object, I basically have to decide what should be the pre-grasp shape of my hand, what should be the grasp shape of my hand, where do I want to put my fingers on the object to be grasped, and how much grasp was. So if we want to execute a manipulation action like picking and placing an object, we have to decide on how to set all these parameters in order to do a motion that achieves the desired effect and avoids the unwanted ones. Okay, and this is exactly what such a robot control system is supposed to do. So if we get as an instruction that the robot should perform a fetch and place task with a cup, and where it should place the cup on the kitchen table, we can take that task request and instantiate our general plan with these information. So at the location where the cup is, I want to fetch the cup. We know from the motion plan that we have just seen that in order to do that, the robot control system has to infer all the motion parameters like the pose of the robot in order to pick up the object, the arm that it uses in order to reach for the object, the grasp type, the lift pose, and so on. So what the robot control system has to do is it has to infer all these motion parameters, and in such a way that the general plan that we have here will be executed successfully, which means that we can achieve the desired effect and avoid the unwanted ones. And the reason that this inference task is so hard, so complicated, is that answering these type of questions competently requires a lot of common sense knowledge. So we have to know that, for instance, clean cups are typically in cupboards. Intuitive physics knowledge. So we have to know if containers are filled, they have to be held upright. Often it requires anticipation. So if I'm picking up an object and I want to avoid to having it recast when I'm putting it down, I have to think about what is the ideal pose of putting it down in order to decide how I want to pick it up. And I need other cognitive capabilities like visual imagination and experience. So the hypothesis that is underlying our work is that we believe that we can equip robotic agents with very generalized plans that that we have seen before. And we can also complement these generalized plans with knowledge, with a knowledge base of generalized knowledge that contains knowledge pieces such that cups used for table setting have to be clean. Clean cups are in a cupboard, or typically in a cupboard. Cups have to be grasped at the outside. We also have to have much more powerful knowledge, which is much more general. So we want to parameterize motions in order to avoid unwanted side effects. So these knowledge pieces are more general, but at the same time, they require a lot more reasoning in order to decide whether parameterization would avoid unwanted side effects or not. Also knowledge like spilling is an unwanted side effect of pouring, and or things that we can learn from experience, like how should I pick up a heavy pot. So if we are looking at that, we basically can write robot control programs that are able to perform tasks like setting the table. And this is essentially the task, the plan that I've talked before. But we can now see that this plan is generating very flexible behavior, a large variety behavior. So it's picking up a milk box out of a fridge, and in order to do that, it has to open the fridge. It's also basically getting from a cupboard the cereal box, and you see here on the upper side the reasoning that takes place inside the robot control system in order to make all these decisions. And it's getting spoons, kind of a bowl out of a drawer, and later the spoons out. And each of these objects has to be grasped in a different way. The robot has to have different action strategies in order to move them. And all these decisions for parameterization are done autonomously by the robot control system through knowledge-enabled reasoning. You see, so this is actually not a bug, but a feature, because the other heavy component that is very important to have in a robot control system is that the robot is aware of failures, right? So that it's actually detecting when it fails and recovering from failures and completing the tasks despite of these failures. And here you see how general that program that we have seen before really is. So in the upper left, you see the robot not setting the table, but cleaning the table. So here it's actually throwing away items in the waste basket. Here you see kind of the same program running for a different robot with very different kinematics. So here we have changed the structure of the environment and the program still works. And here we basically look at a very different problem domain, namely the assembly of a toy plan, and still the same plan is actually controlling the robot to complete the tasks successfully. Okay, so we have seen so that idea of having these very general plans is very powerful, but only if we have a powerful knowledge representation and reasoning system that complements that program. So we are developing a knowledge representation and reasoning system, which is called NORP, which provides the necessary knowledge and inference mechanisms to do these tasks. And kind of one of the key components of that knowledge representation and reasoning system, which differentiates it from, I guess, almost all other reasoning systems, is the so-called inner world knowledge base. So the basic idea, so one of the main problems with classical knowledge representation and reasoning is that it's too abstract. So we are talking about objects only by the name, and actions are conceptualized as state transition systems in an abstract and atomic manner where basically the actions are atomic state transition from one state to the next one. So what we are doing is we are taking that symbolic knowledge base and coupling it with an artificial world. So essentially the artificial world is a scene graph that we know from virtual reality environments. So we take that symbolic representation of the world, we can render it in virtual reality, and we can also simulate the execution of actions using the artificial world. So knowledge bases in our framework are a combination, a pair of a symbolic knowledge base together with an artificial world. So if we want to have that running in a robot control system, of course, the goal is to have that artificial world match very closely the real world. And we want to have that match so close to each other that if we are executing a robot control program in the real world and in the artificial world, you couldn't tell whether the robot was actually executing its plan in the real world and the artificial world from the behavior that it generates. So why do we want to do that? Well, the main reason is if you're looking at the sensor, the perception capabilities of robots, we have only very sparse information about the world. If you look at the artificial world, we have all the details about the artificial world, and we can basically access all information that the robot control program needs in order to act successfully. So if we are getting that match close enough, then we can play a game that we make the robot control program believe that it's acting in the artificial world, but in reality, it's acting in the real world. Of course, that match never happens, right? So we have to complement the robot control program with lots of events and failure detection and continuation in order to manage the discrepancy between the real and the artificial world. But we are very optimistic that this is actually possible. And in one instance, and that is acting in retail stores, we can already show that this is actually working. So here you see a robot going into a retail store and building a knowledge base that I've introduced before. So you see, the idea is that we give the robot knowledge about the products, about shelf systems in general. And now the robot is, so here you see the robot acting in the real world. Here on the right-hand side, you see the belief state of the robot. And you see how it's in the course of time generating the model of the retail store in its belief state. So it started with recognizing the shelf system. Then it has detected the individual shelf. And now it's looking at the individual shelves in order to detect the separators and the barcodes for the products. If it has that, then it can basically look whether the products that are supposed to be there are indeed there. And it basically builds a compositional model of a complete retail store. Without needing to intervene and add semantic knowledge to these knowledge bases, we can then use the model that the robot has acquired as a symbolic knowledge base. And we can ask questions like, where is a particular product? Or where in the retail stores are empty faces that need to be refilled? If we combine the knowledge about the retail store with more comprehensive background knowledge, like which products are health-threatening, so something like the cleaning products, right? Then we can ask questions, where are health-threatening products that are in the reach of kids? But we have also seen in earlier on the slides that we can take these models and rebuild them in virtual reality environments, right? So we go and basically duplicate the real world in a virtual reality world. And now a human can take the virtual reality environment in order to go shopping in the model acquired by the robot. And because this model is a knowledge base, we can also ask all the queries about that and use the background knowledge about that. And in particular for people working on autonomous manipulation robots, kind of the biggest thing is if we can deploy a robot in an environment, the robot can then build a model of the environment and then it accomplishes its tasks based on the model it has acquired. And that's what we are seeing here, right? So the robot basically fills an empty facing in a shelf based on the models that were autonomously acquired by the robot before. And that kind of technology is not only a technology that is working in the lab, but we actually deploy that also to real retail stores, and you see the kind of the sizes of maps and the accuracy you can achieve for these kinds of knowledge bases. Yes, so I think, as you can imagine, so there's a lot to be done, right, until we get that kind of technology and get it working in more open environments like human living environments. And yes, so we all wish that we could actually work together and aim at solving these respective research tasks together. And I think also Gerhard would have loved to work on these problems and push our AI technologies more towards real-world robots solving real-world tasks. Okay, thanks a lot.
Yes, thank you, Amin, for your very, very personal as well as scientifically inspiring talk, Michael. Thank you, Amin. So there is actually a question from the audience. Yeah, so we have a chat going on, and the gentleman who is Mr. Shashank actually likes to know a little bit more about the representation format of the knowledge base. And his question goes into the direction, is it compatible to current graph databases or linked data? So I guess the intention is how much standardized is this representation?
Yes, so
I don't hear
it's basically for linked data is a necessary component of our knowledge-based applications. So if you imagine, so on the one hand side, in a retail store, you want to have the exact geometry of the objects and how they are composed. You also want to have that link to the information systems, to the ERP systems of the retailers, but you also want to have the World Wide Web and the information contained in the World Wide Web in order to get domain knowledge, right? So this way you can think about kind of robotic agents that give advice with respect to diet restrictions and basically exploiting the information about websites like WikiHow or kind of that basically specify the ingredients for certain products, right? And and the game has to be in the long run that robots combine very well-designed knowledge bases with encyclopedic knowledge, with these huge encyclopedic knowledge, with a huge linked open data knowledge bases from the web. And yeah,
may I ask a follow-up on that, because this is an interesting issue. So let's talk about ontologies, for example. You have huge ontologies, and ontology is a very well-established kind of format for knowledge. And can you handle inconsistent ontologies, or does your robot sort of assume that what he reads from his data is always sort of consistent and fault-free and complete and stuff like that?
Yeah, so we are exploring these issues, right? So on the one hand side, you certainly don't want the one consistent ontology, right? And the reason is, if you think about robots and you want to have kind of an outdoor robot, right? So you want to link that robot to knowledge sources like OpenStreetMap, and OpenStreetMap comes with its ontology, right? So whenever you are forcing another ontology, you cannot be a parasite of the developments that go on in very specific domains, right? So the game has to be more like, how can we build the bridges between different ontologies, and can we have an ontology that enables us to use these other domain-specific ontologies that huge communities are already building and pushing, right?
Yes, okay. So there is thank you very much. There is another question from the audience. It's Agnese Ciatti. Yeah, so she asked, within NoRob, have you found certain knowledge types to be more vital than others to support reasoning? For example, domain-specific versus more general knowledge to reason about physics and so on.
So I think for robot, it kind of the knowledge that is most essential is to make explicit the data structures and the computational processes that are already in your robot control system, right? So if your robot control system is doing, for instance, Bayesian estimation for localization, right? So you want to have your symbolic knowledge base to be aware of that, and to ground your symbolic expressions into your into the data structures of the robot control system, right? And this is extremely important, in particular if you're thinking about robots that do manipulation tasks in the world, because there you have to combine the knowledge in your perception system with the symbolic knowledge base, and then with your controllers that are developed in control theory, right? And unless you kind of get a semantic structure that links these different parts, you always have gaps in your robot control system, and things will not fit together, right?
Right. So maybe I ask now a very last and closing question. And of course, this has to go into the direction of deep learning, right? Yes. So the question is, how do you fill your databases? And the answer of Google and Amazon and so on will always be, well, observe the world, collect the data, and everything what you need to know is in the data. And of course, I think your approach is more driven by, let's say, more deterministic, quote unquote, approach. So you have rules, you have maybe CID drawings of the objects, you would know shapes, and so on. So obviously, there is something like a lingering gap between do everything in data or do everything by modeling. So how do you expect that the big data hype, which we have, will help ultimately the robot to perform, to fill its databases better, let's say, to generate knowledge, if you like?
Yeah, so I mean, so for one thing, we are using deep learning within our robot control systems at many different places, right? And the connection is, so what we are opposed to is looking at the whole robot control system as an end-to-end black box, right? And so we think that this is not fitting, right? But if you think, for instance, about the perceptual capabilities and detecting objects or categorizing them. So we believe very strongly that these are heavily deep learning tasks. So the way that that our system is working, in particular, if you keep in mind that we have that link to these virtual reality communities, to the virtual reality infrastructure, is that we are using these knowledge bases that are composed of symbolic and scene graph representation as a way of generating the data for deep learning algorithms, right? So because there you can always get the pair a symbolic expression and say it's rendering in the artificial world, or the physical simulation in the artificial world. And of course, because we are in artificial world, we can also generate the amount of training data that are needed for many of the deep learning tasks. Yes.
Yes. Okay. Yeah, this sounds like a promising way to sort of harvest the best of two worlds. I like your approach with this physical simulator very much. This is a clever way to sort of not rebuild, but sort of ask a simulator instead of trying to map everything what is there. So I think this is a really good way to get hold on what's going on in the real world. But our time is over by now, so we have 11:05 by now. So Professor Beetz, thank you very, very much again for your contribution on scientific as well as on personal side. So it was very, very illuminating, at least also for me. I didn't know about this power of grappa also already in the early days of ICHCA in 1987 in Milano, but a lot of things get clearer now, especially into the direction of Gerhard. And I would like to also thank the audience for being with us today. Please join us again tomorrow at 10 o'clock again, where we are going to listen to the talk of our guest Itsuki Noda from IST from Japan. And he will talk about the pathway from Robocop to applications. So thank you very much and stay tuned. Bye-bye.
Yeah. Thanks a lot. And I'm looking forward to the rest of the symposium. And
Great.
Thanks a lot for organizing that and having that event. Bye-bye.
Again. Bye-bye now. Der Horst hat im Video gestoppt. Juhu!